This is video 12 of the thermo course with Lars Erik. I now start with at the beginning of chapter 11, 11.1, fundamental property relation. And I start with this old equation. This is equation 6. This is for one case and a closed system. In chapter 6, we worked with pure components and one phase and a closed system, and now we will go to an open system. Where the number of moles times G, the total gives free energy, is some function of pressure, temperature, and the amount of N1, N2, and to all components in the system. And then the change in total gives free energy is then the change in all the factors. First, we keep temperature and the amounts constant, and we change the pressure. Then we differentiate with temperature, keeping pressure and all amounts constant, and then we multiply with dt. And then we have this extra, which is due to the open system, that if we add some components, we have to add the change of the property with each component, and we, for each component, we have all the other components constant, and we multiply with the actual. We sum up for each component the change in total free energy per amount of component I, keeping P, T, and all other components constant, and then multiply it by the addition of each component. This is actually only a mathematical expression when we accept that the total gives free energy is a function of pressure, temperature, and all the components. Then we define a chemical potential with μ as a symbol, and we define that as the differential of the total gives free energy when pressure, temperature, and all other components. That I is constant. And to keep the things from each other, so far we have not introduced anything like the partial molar property. We are only talking about the total Gibbs free energy, and we define this chemical potential as the change in total Gibbs free energy with regard to the amount when pressure, temperature, and all other components are constants. So in the beginning here, we have defined partial molar properties, but that is done later in the chapter. And also, the energy is NV dt minus NS dt plus the sum of the chemical potential times the change in amount of each component. And for n equal to 1, dg equals v dp minus s dt plus the sum of the chemical potential times the change in mole fraction of each component. So this is a general equation for the change in Gibbs free energy for an open system. Then in chapter 11.2, we go on to the general statement that the chemical potential and its point to define equilibrium. For a vapor, the change in total Gibbs energy in the vapor is NV for the vapor dP minus NS in the vapor dt plus the sum of the chemical potential in the vapor times the change in the amount of vapor of component I. So this is we use this equation for the vapor, and similar for a liquid, dNg for a liquid is NV for the liquid dP minus NS of the liquid dt, and then we add the chemical potential in the liquid times dNi of the liquid. So we put up the expression for the total Gibbs free energy for the vapor and the total Gibbs free energy for the liquid. Then we have the sum dNg is NV dP minus NS dP plus the sum of the chemical potential in the vapor times the change in the amount of each component in the vapor plus the chemical potential in the liquid times the change in amount of each component in the liquid. And this is equation 6.6. That is a general equation because we have summed up this. And when we have to add that one. So from this follows that the sum of the chemical potential of the vapor times the amount of each component in the vapor plus the sum of the chemical potential times the change in each component in the liquid should be equal. We have that equation and this must be 0. For a system with transfer between vapor and liquid, if we transfer some from the liquid to the vapor, if we transfer something from the liquid to the vapor, then we get a change in the amount in the vapor, and we get a similar reduction in the amount in the liquid. So the change in amount in the liquid is minus the change in amount in the vapor. Then the sum of the chemical potential in the vapor minus the chemical potential in the liquid times the change of each component in the vapor should be 0. And from this follows that the chemical potential for the vapor must be equal to the chemical potential of the liquid for all components at equilibrium. So that is an important equilibrium criterion, and the starting point is that we go from traditional thermodynamics for a closed system. We add for an open system the Gibbs free energy for each component multiplied by the amount of each component. We set up one equation for the Gibbs free energy in the vapor, one equation for the free energy in the liquid. We sum them. Then, because we know that this is always valid, we can delete all these terms, and we end up with these terms. And there is a connection between the change in the change of amount in vapor and the change of amount in the liquid for each component. And then we end up with this equation. And it follows from this equation that at equilibrium conditions, all chemical potentials for every component must be equal in the vapor and the liquid phase. So that is the end.